Sorry, I need to scoop my dog away. Alrighty, welcome back, lads and ladies, to Honors Calc 1. Today we are going to talk a little bit more about net change and displacement. There is one particular problem that I'd like to solve concretely for you. Then we'll do a little bit more practice with integrals, definite and indefinite, and then I'm going to introduce to you gently this thing called the substitution rule, which we will be working with next week. After we get through the substitution rule, which is section 5.5 in the text, we just have one more section before the semester is over, so you're almost there. All right. So let's get started. Today's going to be a pretty quick day. Get a little bit more practice with net change versus concepts like distance traveled. A little more practice with definite integrals. And then we're going to introduce 5.5, which is on the substitution rule. Technically, Calc 2 starts where Calc 1 leaves off in section 6.2. The last section we cover here is section 6.1, which is on areas between curves. But most Calc 2 classes spend a little bit more time here talking about substitution because it's rare that somebody comes out of Calc 1 with a truly strong grasp of it. I strive to make my Calc 1 classes a little bit different because I do so much Calc 2. That's kind of my baby here at the college. I am frustrated by how often Calc 1 classes don't really get to treat this. Some skip it entirely, which is fucking unbelievable. And others like cram it into the last week in a really nasty and haphazard way. So we're going to introduce this gently today. We're going to spend most of next week on it. And then we'll move forward to the 6.1. But before we do that, I want to come back and solve this one particular problem that I'd like to solve here. Ben looked at a slightly more challenging version of this problem in his lecture on Wednesday, and I wanted to come back and look at a slightly easier one just so we had a really clear idea of what's going on there. And then after that, we'll work one or two more problems just with integrals, and then I'll introduce this. Okay, let me get this out of the way. Let's do it. So actually, we don't do this here. Just do it like this. Suppose a particle is moving along a straight path with velocity v of t is equal to t squared minus t minus 6. I want to do two things. I want to find the net change in displacement from t equals 1 to t equals 4. And I want to find the distance traveled Same thing from t equals 1 second to t equals 4 seconds. All right, so maybe this velocity is being measured in meters per second. And these times are in seconds. The first part is not at all hard. We remember from Ben's lecture that the net change in displacement is just the integral. So for part A, the net change in displacement would just be the integral from 1 to 4 of v of t dt, which is the integral from 1 to 4 of, remember, we should always put our integrand in parentheses. So t squared minus t minus 6 dt. And while you could dive in here with a Riemann sum, since at this point we know the fundamental theorem of calculus, you should never have to do that again. And good news, no more Riemann sums. You are liberated from those. The way we evaluate this and any other integral is by finding an antiderivative, right? We use FTC2. We just find an antiderivative and evaluate between these bounds. So our antiderivative here is t cubed over 3 minus t squared over 2 minus 6t, just applying the power rule to each of these pieces. So you increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. And this constant here, whose derivative is 6, well, 6t. Because all of these pieces are separated by addition and subtraction, we can do each one on their own. If they were being multiplied or something like that, then we're fucked and we got to do something else. But remember, antiderivatives, you can split them up over addition and subtraction. So each one of these pieces, I know the antiderivative for. So I can just take each antiderivative on its own because they're just being subtracted. If I plug in 4, I'm going to need a little bit more space here. So if I plug in 4, I get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. And then I subtract what I get when I plug in my lower bound, which is 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. Four cubed is 64. So this is 64 thirds. 4 squared is 16. 16 over 2 is 8. 6 times 4 is 24. And then distributing this negative, I'll have minus 1/3 plus 1/2 plus 6. And I'm not shy about using a calculator to do arithmetic here. There's no reason to beat ourselves to death and waste lecture time. So we've got 64 thirds minus 8 minus 24 minus 1/3 plus 1/2 plus 6. And we get negative 4.5, or as a fraction, it would be negative 9/2. Negative 4.5 meters. And I'd like to ask you guys, what does it mean that the net change in displacement here was negative? What does that tell me? What does that tell me about the physical situation, the particle, the movement?
Is it going left?
It means that it ended up to the left of where it started. So maybe it went left a little, maybe it went right a little bit, but it went further to the left than it did to the right, or it ended up behind where it started. Yeah, my net change in displacement being negative means that I ended up to the left of where I started. If you think of going to the right as the increasing direction of travel. Obviously, the distance traveled isn't the same as this because distance traveled needs to be positive, right? I can't travel a negative distance. I can have a negative displacement, but the total distance I travel should be a positive quantity. Before I move on, are there any questions about any of the steps here? Okay. So then for the second part, for part B, let's say recall what distance traveled. This isn't just the integral of the function, it's the integral of the absolute value of the velocity function. So that's what I would like to evaluate here. It's the integral from 1 to 4 of the absolute value of t squared minus t minus 6 dt. And in order to get a feel for what that is, I should graph this velocity function. V of t is t squared minus t minus 6. And this one does factor nicely, so this is a little easier to see what's going on. This is t plus 2 times t minus 3. So if I mark this as 3, and I mark this as negative 2, then I can see pretty readily that my velocity function is this parabola. The vertex is exactly halfway between negative 2 and 3. That's positive 1. So this is 1. And I'm interested in finding out what happens between 1 and 4. So I'll mark 4 here as well. So the thing that we did in part A was find the integral measuring these areas, but remember the integral measures signed area. So this region being larger than this region gave me a negative value for the integral overall. In other words, what we see is that v of t is negative from 1 to 3, and v of t is positive from 3 to 4. So if I want to get the absolute value of my velocity function integrated from 1 to 4, really what I'm looking for is this area measured as positive plus this area measured as positive. And the way we do that is to split up the integral. You take the integral from 1 to 3 separately from the integral from 3 to 4. I know if I do the integral from 1 to 3, that's going to spit out a negative number. It's going to spit out this area, but negative. In order to account for that, here's what we do. I say, okay, integral 1 to 3 of, and now notice no absolute values, t squared minus t minus 6 dt, but I put a negative here. Because I know that this is already negative, in order to make it positive, I slap on another negative. And then to that, you add the integral from 3 to 4 of t squared minus t minus 6 dt. This one function was already positive here. This is coming from the definition of absolute value. Remember, absolute value of some stuff is that stuff if that stuff is greater than or equal to 0, but it's the negative of that stuff if that stuff is negative. So v of t is negative from 1 to 3. So the absolute value of v of t between 1 and 3 is actually negative v of t. So this negative right here is coming from the absolute values here. You guys feel like you understand this setup? Cool. Okay, then from here, there's nothing to do but to compute. And the antiderivative is the same. This is not a terribly difficult thing. This is going to be negative bracket t cubed over 3 minus t squared over 2 minus 6t evaluated from 1 to 3 plus bracket t cubed over 3 minus t squared over 2 minus 6t from 3 to 4. And then we do the normal thing here. I'll plug in my upper bound. So we're going to 3 cubed over 3 minus 3 squared over 2 minus 6 times 3 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. That's all from the first evaluation bracket. All of this is this. And then plus what I get from here, which is going to be 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. And now there's a big mess of arithmetic to do. Let's see what we can get. I'll simplify a little bit and then we'll turn back to the calculator to help us out. 3 cubed over 3 is 9, right? It's 3 squared. So this is 9 minus 3 squared over 2 is 9 halves. Minus 6 times 3 is 18. Now I'll distribute this negative. Minus 1/3 plus 1/2 plus 6. So if the function is hard to graph, Ben asked an interesting question. If the function is hard to graph, there are other ways to figure out where the function is positive and negative. Now, we don't need critical numbers necessarily. Remember, critical numbers are places where the derivative of that function is 0 or undefined. But you would need to find where that original function is 0 or undefined, and then make a number line for that original function. Yeah, instead of drawing the graph here, we could have factored this and made a number line. Right, the number line for v would contain just -2 and 3. And we would discover that the function is positive here, negative here, and positive here. And that would have told me, okay, well, from 1 to 3, v is negative, and from 3 to 4, v is positive. Lower bound for the second guy. Oh, did I write 1s here? Yeah, these should be 3s. I'm so sorry. Thank you for catching that before it went further. Yeah, the lower bound here is 3, so these should be 3s. Thank you, thank you. All right. And then over here, 4 cubed is 64, so this is 64 thirds, minus 4 squared is 16. 16 over 2 is 8. 6 times 4 is 24. And then I'll distribute here. Again, 3 cubed over 3 is 3 squared, so this is minus 9. And then minus minus here will make plus 9 halves. and then plus 18. And then each of these pieces we can crunch out. No, could you feed in a second? No. I'll do it after class. So what we'll have here is 9 minus 9 halves. I'm just going to go ahead and put this in. 9 minus 9 halves minus 18 minus 1/3 plus 1/2 plus 6. And I'll write this down. We can write it as a fraction. Negative 22/3. So this piece here is negative of negative 22/3. And then here we have plus 64/3 minus 8 plus 24 minus 9 plus 9 halves plus 18. And again, ratio, that is 17/6. So what we see, cover up this negative for a second, what you see is that from time t equals 1 to t equals 3, the particle traveled left 22/3. And then from time t equals 3 to t equals 4, the particle traveled to the right 17/6. Now this is larger than this, so we did go more left than right. But if I want to know the total distance traveled, that's this number made positive, and that's the purpose of the negative out front. So if you take 17/6 and add to it 22/3, you get about 10.16 or 61/6 meters. So what happened here is the particle was moving to the left at first, right? From time t equals 1 to t equals 3, the particle was moving to the left. And then at time t equals 3, it turned around and started moving to the right. And it moved more to the left than it did to the right. This area here is larger than this area. So my displacement was negative, but my distance traveled should always be positive. Questions on this example? It's very similar to the one Ben did the other day. I just wanted to grind it out explicitly. Well, they told me they wanted to find the distance from 1 to 4. Right? So from time t equals 1 to time t equals 4. So this is the integral I had to do at the start. In order to do this integral, I drew the graph of v of t, and that's where I got the 3. So the 3 is where my function goes from being negative to being positive. That told me to split it at 3. Because from 1 to 3, my function is negative. So I do the integral from 1 to 3, and I slap a negative out front to make that positive. And then separately, I do the integral from 3 to 4, and I don't have to do anything special there because my velocity function is already positive. So the 1 and the 4 came from the problem. The 3 I had to find through graphing, or factoring a number line if you prefer that. So drawing the graph here is very helpful. Other questions on this one? Okay. So I would like to look at just one or two more problems evaluating integrals. There's a few good ones in here. Let's look at number 39. That's the integral from 1 to 8 of 2 plus t over the cube root of t squared. Okay, who can help me out with this?
So you move the denominator, the cube root of t squared, up to the numerator, and then distribute it.
So before I move this upstairs, there's something else we should do. That is a fine way to think of it, sure. But how would it look as it came upstairs? I think splitting it up is a really good idea too. So there's a couple ways to approach it. Either Ben's approach or Julio's approach would first require rewriting this as a power though. So this is 2 plus t over t raised to what power? What is the cube root of t squared? Yeah, t to the 2/3. So I would certainly begin like this. And then you could take either approach. You could bring this upstairs as t to the negative 2/3 and then distribute. And that would get you the same thing as if you take this as 2 over t to the 2/3 plus t over t to the 2/3. Same result. Sorry, we're still dealing with the very friendly but very annoying feral cat from the neighborhood. So let's try splitting this up. This would be 2 over t to the 2/3 plus t over t to the 2/3 dt. And if you think about it, that's the same as 2 times t to the negative 2/3 plus t times t to the negative 2/3. It's the same thing you would get by bringing this upstairs and distributing.
Lecture.
But now before I can continue, I need to simplify each of these pieces. So I have integral 1 to 8. 2 over t to the 2/3 is 2 times t to the negative 2/3 plus t over t to the 2/3. The rule I'm using here is t to the a over t to the b is t to the a minus b, would be t to the 1 minus t to the 2/3, which is t to the 1/3. Everybody on board so far?
Yeah.
And if we pulled this upstairs as t to the negative 2/3 and distributed combined powers, this is what we would get. So whether you take Julio's route or Ben's route, we all land here. What do I do from here?
You take the integral of each one.
Yeah, I need an antiderivative for each of these guys. So this too is going to come along for the ride. And then by the power rule here, I add 1 to this power and then divide by that new power. So negative 2/3 plus 1 is positive 1/3. So this will be t to the 1/3, and I divide by that new power, right? That's like x to the n plus 1 over n plus 1. And then I do the same thing with the t to the 1/3. If I add 1 to the power 1/3, that becomes 4/3. So t to the 4/3 divided by 4/3, and all of this gets evaluated from 1 to 8.
Yeah, I don't mean to interrupt you.
Oh, no.
It was actually Kevin's suggestion, like before.
What was the comment there, Julio? I'm sorry, I couldn't hear the end.
Oh, so you asked how should we approach the problem? It was Kevin that answered, not me.
Oh, I'm
Yeah,
sorry.
yeah. I mean, I think he's talking about the first suggestion when I like suggested moving it up to the numerator, but it's no big deal.
I'm sorry. Yeah, I was going based on voice there. For some reason, Kevin sounded like Julio.
Nah, you're good. You're
Sorry.
good.
All right. So from here, I would like to simplify this and this a little bit before plugging in these bounds, make my life easier arithmetic-wise. Dividing by 1/3 is the same as multiplying by 3. 2 times 3, this is 6 t to the 1/3. And then over here, dividing by 4/3 is the same as multiplying by 3/4. So this is 3/4 t to the 4/3. And now I go ahead and plug in my bounds. So if I plug in 8, I'll have 6 times 8 to the 1/3 plus 3/4 times 8 to the 4/3. And from that, I subtract what I get when I plug in 1, which is going to be 6 times 1 to the 1/3 plus 3/4 times 1 to the 4/3. And the last thing to do is just simplify these powers a little bit. What is 8 to the 1/3 power?
It would be
2.
Yeah, it's 2, right? The 1/3 power is the same as the cube root. 8 is 2 cubed. So 8 to the 1/3 is 2. And that'll also help us with this other piece. So this piece is 6 times 2. And then here I have plus 3/4. 8 to the 4/3 is the cube root of 8 raised to the 4th power. So that's 2 to the 4, which is 16. And then over here we have minus 6 plus 3/4, because 1 raised to any power is just 1. We can clean up a little bit more. 6 times 2 is 12, plus 16 divided by 4 is 4. 4 times 3 is also 12. And then here I'll have minus 6 minus 3/4. So 24 minus 6 is 18. 18 as a ratio over 4. I'll be lazy again here. Why not? 18 minus 3/4, which as a ratio is 69/4. So that's where we end up. Not too bad, right? Not too bad. Certainly better than building a Riemann sum for this thing. And really, it's mostly about the algebra. Right? The calculus step, there's only one calculus step here. Only place we do any calc is right here. From here to here, we applied that little power rule. Everything else is algebra. So these algebra skills need to be tight. They need to be solid. And that's pretty much the game here. There's not much more I wanted to do today besides introducing the material in 5.5. So are there any questions on this example? Seems like
I was wondering, like, how you would have, wouldn't you have to like visualize the graph so that you would know which parts would be negative or positive before you take the integral?
So on that previous problem, since we have the graph, I mean, so the function is negative anywhere it's beneath the x-axis, right? Or in this case, beneath the t-axis. So we factored to find the x-intercepts, in this case, t-intercepts. And that told me these 2 points, the 2 and the 3. And then I knew I was looking from 1 to 4. The problem said we're going to try to find the distance and displacement from 1 to 4. So the trick to finding out where the thing goes from positive to negative is to factor. Is that what you're asking?
Yeah, I understood it in this one, but on the other example, like how would I know when the function, you would have to like actually draw it first to know when the function goes from negative to positive.
That would be the idea. Yeah. If the thing you're looking at, like the example from Ben's lecture the other day, was also a quadratic, so its graph is also a parabola, but the roots were irrational numbers, so they were a little bit gnarly to find. But you could still apply the quadratic formula and find those x-intercepts. The problem we just did, here we weren't looking at any physics things, right? We weren't asked to find like a displacement versus a distance, so we didn't have to worry about any sort of things. But you could see, if you wanted to, that this thing is gonna, the only place where this function can go from positive to negative, there's 2 of them, is at where the top is 0, which is -2, and where the bottom is 0, which is at 0. Now, for lots of reasons, we have to stay away from where the bottom is 0. But if I asked you to find, if I gave you this as like a velocity function, and I asked you to find the distance traveled, you wouldn't, let's see, so you wouldn't have a problem there because the only place where this thing changes from positive to negative is at a -2, which isn't between 1 and 8. So let me try to see if I'm understanding what you're saying. Like
I
in general, go ahead, sorry.
Yeah, no, you answer my question.
Okay. Yeah, the graph is your best friend. Draw the graph if you can. Is there anything else? Any other little odds and ends we could talk about here that we should before we move further?
It's kind of an off-topic question, but I was just wondering, like, if the final exam for sure is going to be like on the 28th, like the syllabus says, like,
Yes.
there's no room for change there.
Not really, no. The final exam dates are set by the college, and those are pretty stern. Under certain circumstances, we can offer a makeup final, but we would need some advance notice and we would need a real solid reason for it.
All right, cool, thank you.
Okay. Are there any problems here that look intimidating to you guys? Any problems that you would like to take a look at? Any of these integrals that look scary, anything like that? These are kind of fun, where you're dealing with an absolute value function again. Just for shits and giggles, let's look at the integral from 0 to 2 of the absolute value of 2x minus 1. We'll do this quickly and then I'll move on. I'll never forget my complex analysis class, which is like a slightly grown-up math class, gave a problem like this on the first exam and a bunch of kids bombed it. It was pretty sad. But here's another thing that could be interpreted as a distance, right? If your velocity function was 2t minus 1, then the distance traveled from time t equals 0 to t equals 2 would be this integral. Again here, it's best to draw the picture. So 2x minus 1 is a line with slope 2 and y-intercept -1. He is pretty easy to draw. Look at something like this. And we want the integral of the absolute value from 0 to 2. So I'll pretend like this is 2 here. I just heard him, I think, out front. Somebody was making noises. Of course, 0 is here at the origin. So if we were to just ignore the absolute values, it would measure this area as positive and this area as negative. And in order to figure out where we need to split this up, I need to know, where is this? So where does 2x minus 1 cross from being positive to negative? Well, 2x minus 1 is equal to 0, right? This is an x-intercept, so this would be a place where 2x minus 1 is equal to 0 when x is 1/2. Yeah, very good. So the game here is to split the integral up at 1/2. I would take the integral from 0 to 1/2 of 2x minus 1 and negate it, because this would be measured as negative, and if I slap another negative on that, that will make it positive. And then I add to that the integral from 1/2 to 2 of 2x minus 1 dx. And I don't need any sort of negatives there because that region is already positive. The function is positive from 1/2 to 2. All right. So then again, antiderivative stuff. Antiderivative for 2x is x squared. Antiderivative for 1 is x. This is x squared minus x evaluated from 0 to 1/2 plus same antiderivative, x squared minus x evaluated from 1/2 to 2. And if I plug in 1/2, here I will get 1/2 squared minus 1/2 minus 0 squared minus 0 plus 2 squared minus 2 minus 1/2 squared minus 1/2. One half squared is 1/4. 1/4 minus 1/2 is negative 1/4. And then these zeros are all 0. 2 squared is 4. 4 minus 2 is 2. So this is 2 minus 1/4 minus 1/2 is negative 1/4 again. So this is going to be plus 1/4. So I get positive 1/4 plus 2 plus positive 1/4. Which is 2 plus 1/2, which is 5/2. And if I asked you for the area bounded by the function 2x minus 1 from 0 to 2, this would be the answer. Because we want to measure the area, not the signed area. There's a little subtlety there. All right, I think that's enough practice with this stuff. I trust that you guys are fairly comfy with it. I guess before it is, any questions on this guy? All righty. So what I do want to talk about now is just a little bit an introduction to 5.5. Like I mentioned earlier, substitution is one of those things that's really important for Calc 2. We use it all semester long. We use it constantly. And Calc 2 professors are supposed to be able to assume that you guys are already rock stars at it when you walk in the door. I'm going to help you make sure that's true. This is section 5.5. I want you to consider the two integrals integral from 1 to 2 of the square root of x minus 1 dx, and the integral from 0 to pi over 4 of sine 2 theta d theta. In each of these, an antiderivative is not immediately obvious. If you were going to take a regular derivative, they would both require the chain rule, right? There's like an inner function here and an outer function. An inner function here and an outer function. And it's not immediately clear how to find an antiderivative. Certainly neither of these show up in your antiderivative tables. If we try to interpret, let me focus on this one first. If we try to interpret in terms of areas, the graph y equals the square root of x minus 1 looks like this. It's half of a sideways parabola, that would be root x, shifted to the right 1 unit. So the thing we're looking at there is this area. And the challenge in terms of the integral, finding an antiderivative, is the minus 1. If this was just root x, then that's x to the 1/2. We know how to find an antiderivative for x to the 1/2. But I don't know right away how to find an antiderivative for x minus 1 to the 1/2. You can't distribute the power. Remember, powers never distribute. You can't like FOIL it out because the power is not a positive integer. Can you think of, though, another graph whose integral would be easier, but would have the same area?
Like the sideways parabola.
Yeah, what if I just move this back over to the origin?
Oh, so ln of x.
Not ln of x. Remember what we said, this guy is the square root function shifted to the right by 1. Well, what if I just undo that shift?
Oh, yeah, you get the square root of x.
Yeah, this is just the regular square root function. So this is down here, y equals the square root of x. And I think we would all agree that the area here is the same as the area here. Right? It's the same curve. It's just shifted to the left, shifted back over to the origin. Only now it's from 0 to 1. So instead of doing this integral, I could integrate from 0 to 1 the regular square root function. The catch is the way we normally do this, instead of writing y equals square root x, we call this y equals square root of u. I want to use a different variable. So I think of this as the u axis as opposed to the x axis. Those areas are the same, so the integrals will be the same. Here's how we do it. It's called making a substitution. Another word for this is a change of variables or a change of coordinates. I'm going to transform this region into this region by making the substitution u equals x minus 1. every time you do such a substitution, there's two things you need to do. We always calculate the differential. Remember when we talked about differentials? This is why. And remember I said I don't really care about using differentials for approximation purposes. I just need you to know how to calculate du. You differentiate this thing. The derivative of x minus 1 is just 1. So du here is 1 dx. That's the first thing you need to do. The other thing you need to do is alter the bounds. My old bounds, my bounds for x were from 1 to 2. When x is equal to 1, we need to find out what u is. Now we already know from down here that the new bounds are going to be 0 to 1, but think about it. If you plug x equals 1 in here, u is going to be 1 minus 1, which is 0. And when x is equal to 2, my old upper bound, u would be equal to 2 minus 1, which is 1. So what that tells me is that I can transform this integral into the integral from 0 to 1 of the square root of u du. I just plug everything in. My old lower bound is 1, my new lower bound is 0. So this 1 becomes this 0. My old upper bound was 2, my new upper bound is 1. So that 2 becomes this 1. The square root of x minus 1, if I'm substituting u equals x minus 1, just becomes the square root of u. And since du is equal to 1 times dx, it just says du equals dx. So this dx is the same thing as this du. And now this is an integral that I know how to do. This is integral 0 to 1 u to the 1/2 du. If you add 1 to that power, it becomes 3/2. So I have u to the 3/2 divided by 3/2, evaluated from 0 to 1, which is 2/3 u to the 3/2, evaluated from 0 to 1, which is 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2, which is just 2/3. And that's the magic of substitution. It takes us from an integral we didn't know how to do to an integral that we do know how to do. And what we're really doing is changing the coordinate system. This is sort of the simplest kind of substitution. It's just a translation. We're just shifting things over. But the other integral here, the sine of 2 theta integral, he's a little bit different. So first I'll take questions on this first guy. Any questions about what we did here? Okay. For the next guy, I want to spend a second in Desmos because the graphs there are a little tougher. You know what sine x looks like. We know what sine 2x looks like, but let's just, here's sine of 2x. And what we want is the region from 0 to pi over, what do you say, pi over 4. So the second integral up there is measuring this area. The challenge is the 2x, or it's a theta on the page here, right? The challenge is the 2 theta. If this was just sine of theta, I know how to integrate that. I know an antiderivative for sine theta. So if I think of a different function, g of x just sine of x, and I look at the region here, The purple region here is not the same as the blue region. These are different. But if you were to remember, sine of 2x is what you get when you take sine of x and you just squish it down by a factor of 2. So if I took this purple region and squished it down by a factor of 2, it would become this blue region. In other words, the purple region here is exactly twice as large as the blue region. Or if you want to think of it in terms of little rectangles, if you take all the little rectangles for the purple region and you chop them in half horizontally, you'll get all the little rectangles for the blue region. The good news is that the substitution procedure is fairly mechanical. So even without the graph, we can run through the same thing we just did. Integral 0 to pi over 4 sine of 2 theta d theta. Again, I have an inner and an outer. And I want to substitute for the inner. Sure. Yeah, we want to look a little more at this. All right. So again, I want to substitute for the inner function. Substitute u equals 2 theta. And I need to begin by calculating my differentials. Now this time du is not just going to be the same as d theta. If I differentiate 2 theta, the derivative of 2 theta is 2. So du here is 2 d theta. And I need to alter my bounds. When theta is equal to 0, u would be equal to 2 times 0. 2 times 0 is still 0. When theta is equal to pi over 4, u would be equal to 2 times pi over 4. 2 times pi over 4 is pi over 2. So those are my new bounds. Let's see what we get if we start trying to plug things in. Integral 0 to pi over 2. Sine of 2 theta is going to be the sine of u. But now I run into the issue. D theta is not just equal to du. Du is equal to 2 d theta. So you need to come back here and solve this for d theta. If you divide both sides by 2, or multiply both sides by 1/2, you'll see that du equals 2 d theta is the same as saying 1/2 du is equal to d theta. So as I'm plugging things in here to change over from the variable theta into the variable u, my bounds change, my integrand changes, and my differential changes. D theta is not just du, it's 1/2 du. And remember, the differential is multiplying. That's how it works. And this is exactly what I was saying about the widths of the little rectangles, right? Each of the d theta tiny little rectangle widths is 1/2 of the little du widths. So if I pop this 1/2 out, and I can do that because it's a constant multiple, I'm left with an integral that now I know how to do. And this is the magic of substitution. The little change of variables can take an integral from very, very hard to very, very easy. An antiderivative for sine of u is negative cosine of u. So that's what I need to evaluate from 0 to pi over 2. In doing so, we get 1/2 negative cos of pi over 2 minus negative cos of 0. What is the cosine of pi over 2?
0.
Good, 0, right? It's unit circle stuff. Cosine of 0?
It's 1.
Good. So I have negative 0 minus negative 1. So that's just 1/2 times 1, which is 1/2. And again, this is the magic of substitution. Now, the thing that people make mistakes on here, they forget to change the bounds. No excuses for that. You got to do it. And they forget to do the differential stuff. So pick your substitution and then immediately calculate your differential. This sitting here will remind you to do this later. After you do that, change your bounds. Then start plugging things in. Old integral, old bounds, new integral, new bounds. Plug in your u, and then look and see what d theta or dx, your old differential, becomes. That's when you come back here and you solve this for your old differential. The most important thing is that before you take your antiderivative step, you've changed every single piece into the new variable. You cannot have sine of u d theta and then take an antiderivative. It doesn't work. You need to change everything over. And if there were any other bits associated with the variable theta floating around at this stage, we would need to go back and replace them with the equivalent expression in terms of the variable u. So these two examples are kind of as simple as possible to serve as an introduction. And then next week, I will show you guys the full substitution rule and in all of its beautiful detail. And we will work forwards from there. So that's all I've got for you guys today. Any burning questions before I let you go? Alrighty then, today will be a little bit of a short one. I hope you guys have a wonderful weekend and I will see you back on Monday.